So, yeah, as Ilaria said, I'm kind of in this dual bimodal behavior right now where sometimes I'm CTO of Duality Technologies, sometimes I'm a professor at NJIT, sometimes I'm both, a superposition principle or something like that. So this talk is mostly NJIT, but a little bit of both at times also. And you know, plenty of contact information there if you ever want to get in touch with me. So I know that I looked on the agenda, it looked like there was actually going to be a number of talks related to homomorphic encryption like there was before. And originally I was actually planning on talking about homomorphic encryption also and some of the work that we're doing. And then I decided that, you know, I'd try to do something a little bit different that we've been kind of coming up with the past couple of years. It's a little bit more experimental and out there as compared to homomorphic encryption. So, you know, what I am, so I'm not a cryptographer at all. You know, I got into cryptography, as they say, euphemistically by side channel attack. I'm actually an engineer by training, which means that I got into homomorphic encryption and lattice-based crypto because I build things and I build software libraries. And I have this open source library called PALISADE, which, although I call it mine, it's very much a collaborative effort. And you know, I've been basically trying to build anything and everything that's lattice-based crypto, either into or part of or on top of PALISADE. And there was a project that we were sponsored to do for several years, experimenting with software obfuscation, program obfuscation, cryptographic approaches to program obfuscation with some prototype results. And that's one of the things I want to talk about today, but also how we've actually been implementing it and building out this PALISADE open source library to go and do these things and use them. So, you know, this is where this kind of dual hat comes out, where there's a fair bit of stuff on the academic side of my life, primarily sponsored by DARPA and other kinds of organizations in the United States, and also the commercialization of these various kinds of open source activities through Duality, split between Israel and New York City. And you know, I'd be remiss without coming all the way over here to say that, hey, at NJIT we're hiring, and if I'm sorry. So if you want to stay in Leuven, beautiful Leuven, please don't talk to Nigel. If you want to come to the big city, we're hiring in New York City too. You know, options for all different strokes for different folks, as we say in the US. And I'd also be remiss if I didn't say, hey, we're hiring for Duality also. So, you know, if you don't want to be a student anymore, come talk to me about that later. So, you know, we were talking earlier about homomorphic encryption. I don't think I really need to define it, but, you know, I got my academic hat on, so, you know, everything should be defined at some level or another. And so, you know, we're probably familiar with the usage model of homomorphic encryption, which is that you have a client, you have a data source, you have a computation host, you push around some public keys, you do some encryption, do some computation on that data, send back the result, and then decryption to get a decrypted result. You know, all well and good. Well, you know, this solves a lot of problems. It's not a panacea. It doesn't solve every problem, but it does a lot of nice things in terms of data privacy and confidentiality and things like that. Well, there's a converse problem, whereas what if the actual computation that you want to run is sensitive, which is a fairly common use case. There's a lot of examples of this, of organizations, fintechs, AI companies that'll build up some sort of classifier. They want to go and deploy that classifier some way or another, and doing it in a protected manner so that provides the classifier from becoming reverse engineered. And this was kind of the vision, or at least how program obfuscation started to become something sort of real in some sense or another. And this is actually what I want to talk about cryptographic program obfuscation, at least lattice-based approaches to it, and how we've been implementing it and prototyping it and accelerating it in a research branch of the PALISADE library also. And I know this is a bit in vogue with the theorists a few years ago. I know it's not as much in vogue with the theorists, but it still, you know, has a lot of these really, really interesting engineering and design challenges that precipitated a lot of advances in the PALISADE library, which is why I'm particularly enamored of talking about this, just because, engineers got to engineer, as they say, and we want to go and build things and make them as fast and as usable as possible. And we thought this was a really exciting target to go after. So like I said before, there's this general problem. What happens when you want to protect the computation? So for example, you might do extensive work to go and train a neural net. Waymo through Google had this big to-do with Uber about extensive work training various kinds of neural nets and machine learning and AI type techniques. But once you actually go and deploy this classifier, basically anyone could steal it, reverse engineer it, and FHE won't necessarily protect you if you want to have the results in the clear. And there's all. What I found. Oops. Never, ever, ever say Google when you got an Android phone with you when you're giving a talk, right? Apologies. So once you go and deploy a classifier or something like that, anyone could go and steal it, reverse engineer it. Apple could, for example, reverse engineer the apps on the phone and so forth. And so there's this general challenge of, can we design programs that can't be reverse engineered? Can we compile software? Because compiled software can be decompiled. Any large organization worth of salt can go and do that. And I'm not talking about like GCHQ and NSA and the like. I'm talking about places like NVIDIA and bread and butter tech firms have piles of people that can decompile and reverse engineer software. And up until recently, until these cryptographic approaches were taken, these obfuscation techniques were mostly heuristic, things like randomizing memory address spaces and stuff like that, things that really, really don't work if you have half a clue about what you're doing. And so the challenge is, can we design software to effectively be something kind of like a cryptographic black box? So I know the term black box is a bit loaded in this community also, and provide some sort of guarantees about reverse engineering. So the general model that we had is that, can we take something like a set of security parameters, stuff it into a key generator, something kind of like a key generator, generate a bunch of keys, and then take some sort of program, and I'm hand-waving what we mean by program for now. Effectively think of it as kind of like a finding state machine, regular automaton, or regular language classifier, regular language acceptor, things like that. And to take those cryptographic keys, take the pattern through there, through an obfuscator, kind of like a compiler, Java bytecode machine, things like that, and generate an obfuscated program, which you might euphemistically think of as something kind of like Java bytecode, but extra, extra secure. And then you take that obfuscated program and go and deploy it. And when you deploy it, I just dropped. When you go and deploy it, you basically run that obfuscated program on an evaluator for some sort of given input, and then basically give some sort of output. And this might be, for example, application might be, you have a medical image that you want to identify, is there a tumor in that image, or is there a certain criminal that's in a CCTV capture or something like that. And output is 0 or 1 if the classifier goes and fires. And like I said, the application for this is that hardware can be captured, stolen, purchased. And the general notion for a lot of our sponsors is that hardware is actually generally pretty darn cheap. You think about these things. It actually is software that is shockingly expensive. And more than that, the actual distillation of data into classifiers and AI systems is shockingly expensive. It takes real human decades, human centuries, FTE centuries, to go and build classifiers and things like that. And so do we want our adversaries to be able to reverse engineer these autonomous systems without having to, actually protect ourselves? So one application that we were looking at for quite a bit was this application of biometric matching. can we obfuscate a program to match faces, irises, fingerprints to a signature of interest? And the example might be, for example, you want to log into your phone. Well, you take a shot of your iris and use that as basically your password, but you don't want an adversary who captures your phone to get your iris signature to get into other kinds of systems and stuff like that. Practicality has always been a major challenge of this. And it's kind of like when you talk about the early days of homomorphic encryption. Early days of homomorphic encryption, you would encrypt 2 bits, run a bitwise AND with a bootstrap. You know, the old story from IBM is that their first implementation took like something like a half hour to run that bitwise AND. When we did our very, very, very first implementation of these obfuscation techniques, cryptographic obfuscation techniques, I want to say around 2015, 2016, give or take, we were talking about like weeks or months for something that was roughly computationally equivalent to doing a bitwise AND. I'll get to a punchline of how fast we're actually doing somewhat more recently now. But like I said, it's a obfuscation vision of taking an arbitrary program and obfuscating it into bytecode, converting like we do with Java and things like that. And there have been a number of milestones about these on the theoretical side. Brock and friends showed a general purpose virtual black box obfuscation is unachievable, but he introduced the concept of indistinguishability obfuscation, otherwise called I/O. Caron, Lapointe, Tabucci proposed the use of multilinear maps for encoding over the integers for I/O, and we did spend a lot of time looking at multilinear maps. I know that's so 2015 now, but they were kind of a thing at some time. And then GGH, Garg, Gentry, and Halevi was looking at further use of multilinear maps for a while. And then another set of GGH, the different, swap out Garg for Gorbanov, proposed graph-induced multilinear maps based on lattices. And all these constructions were broken from the perspective of general purpose I/O and so forth. So that's the state of the literature for there. But there have been some improvements on, and what actually we decided to actually try to build on for this was Vinod and friends, Vinod Vaikuntanathan and friends, had a entropic LWE result for I/O that we decided that we want to try to build up. And so there have been a number of various results on this related to, for example, branching programs that would take, for example, 9 hours to obfuscate with 60-bit security, and program size was on the order of gigabytes, and runtime for actual evaluation was on the order of hours. There was a pile of others, like kind of a similar genre, that were similarly secure and similar runtime on the order of terabytes and days, and so on. We started to obfuscate things fairly early on, and this is a paper that we had in S&P where program size not quite a terabyte and evaluation time of a few seconds. So we're getting there. Memory was cheap, but not that cheap. But we're working on it still. And so we started to look at this entropic LWE approach to go and do things like obfuscate finite state machines, certain classes of finite state machines. And I was particularly interested in this. This is a little bit of an aside. How I said, I'm not a cryptographer by training. I'm actually have a PhD in control systems and actually SCADA control systems. And if you go look at kind of state-of-the-art SCADA control systems, they're basically all finite state machines at some level or another. And these things are pretty widely used in industry, particularly for things like factory automation and a lot of what we in the US euphemistically call safety critical systems. Basically things that keep planes flying and heart monitors beating and stuff like that. So here's a really simplistic example for academic discussion. And suppose you have a pattern, a regular expression, that has an input pattern of 1, wildcard, 0, and 1. And this pattern, this regular expression, you can represent as a finite state machine. You start, if you get an input of a 1, you go to the top. No matter what happens, you move over 1. Input is 0, you go over 1. Input of a 1, then you output, hey, that pattern was accepted. Anything else that doesn't fit that pattern outputs a 0. And so this is a finite state machine with a single accepting state, and effectively operates as a classifier for that regular expression up there. So it's a fairly simplistic pattern that has some meaning for safe control systems. And so when we start to think about these things as actual programs themselves, as being basically a state machine, is that it's what we call a Moore machine. I think it's a Moore machine. I get Moore machines and Mealy machines confused. Input bits drive state transitions. They represent the state transitions as multiplications of ring elements. And so this approach that the Vinod came up with is that basically what we do, kind of like the really, really high-level hand-waving approach to obfuscation, is that every state transition you think about as having a different noise signature. And if you multiply the path that goes from start all the way to the output, the theoretical thought was that if you can define a unique noise signature of the path from start to output of 1, that could define something kind of like what we mean by an accepting state that could be represented in some sort of cryptographic manner. And so the way we start to do that is we start to represent these state transitions as noise samples over matrices, and then we basically multiply these various matrices as state transitions occur to get to this output state. And if the output state has a noise signature within some delta, multidimensional delta of a reference, well, that is an almost surely representation of the state was actually accepted. I know it's a little bit of a hand waving, but I'll get to the punchline of what it actually means for implementation. And please ask me questions as I go through also. So this state machine that we had before, we could represent as each transition, we could represent as pairs of matrices. Each of these matrices are ring elements. Each index of the matrices are ring elements that encode the state transitions. Each has its own noise signature that's unique. And so we can take the accepting pattern along the yellow there in the top with its own noise signature. And this is how we do the evaluation. And we select the corresponding matrices. So if, for example, the input pattern, input evaluation that we want to go and evaluate is a 1, 0, 0, up to a 1, we go and select the corresponding matrices to do the evaluation, which we do right there. So we go then and compute the product of those matrices of ring elements. You get the product of the light blues, you get the product of the dark blues. Take those products, effectively compute something kind of like a cross product, and multiply it by a public key, which is another sample of ring elements. Excuse me. And if the result is small, as in the distance between the side over there and the side over there is small, then that's an indication of the program should accept 1. And these things can get really challenging from a number of perspectives, because when we were looking at the initial sizes, the sizes of the ring elements were on the order of multiple hundreds of thousands of dimension. And the matrices themselves were on the order of 1024 by 1024 matrices. So think about that. 1024 by 1024 matrices Each entry of the matrix is a ring element of multiple tens of thousands dimension. So really, really, really large programs for doing these kinds of things. To the point where in 2015, we were starting with estimated runtimes, key generation that would take 3 years, key size that would be on the order of petabytes, program size on the order of 600 terabytes, obfuscation time of 70 hours, and evaluation time of 9 hours. So you want to talk about secure. It's so secure you can't run it, right? That's 2015. Some recent results, and I think we actually might have things that are a little bit more recent than this, is that we actually were able to get down to key generation time of 100 milliseconds, key size of 1 megabyte, program size of 5 gigabytes, obfuscation time is 6.2 minutes, evaluation time of 32 milliseconds. You know, it's all about evaluation time at some level. And the question is, well, how did we do it? I think the answer to that is, how did we not do it? You know, it's like, you know, it's kind of like the advances of homomorphic crypto. Why has homomorphic crypto gotten so much faster in the past decade? Theory, security level analysis, better sampling methods, you know, better parallelism. It's like you throw the bucket at these things, and so eventually they crack open eventually. And this is, you know, why now someone who's not a cryptographer has become so enamored of lattice-based crypto and lattice-based crypto systems. You know, I've been through a couple cycles of this between obfuscation and homomorphic crypto and so on. It just always seems to be an order of magnitude somewhere that you can get somewhere somehow to actually make things better. The primary actually benefit for this was a lot of work being done by particularly Daniele Micciancio and a couple of his students about how we can actually make sampling much, much more efficient and going forward from there. And so if you want a good read, and particularly I know there was a lot of talk before about how we do sampling better, more efficiently, and so forth, it's been spilling out of there. And particularly it came out of dramatically improved lattice trapdoor construction and sampling algorithms. And we basically use these, and this is kind of another nice thing about this, is that we've basically been using it for more efficient GPV signatures, along with a pile of different ABE, KP-ABE schemes, and so on and so forth. I'm particularly interested in the KP-ABE going forward. I still think it's a couple orders of magnitude away, but as they say, there's so many hours in a day to actually work on a problem. The challenge, though, is still, how do you practically implement more complex functions? And this is kind of the state of I/O right now, at least I/O implementation using these entropic LWE approaches, is that, you know, we can go and obfuscate any program you want as long as it's a special class of finite state machine, which is good for some applications, but, you know, not for a lot of them. And there's, of course, this perennial question of, is it possible to build general purpose obfuscation instructions that can't be broken? I know a lot of the theorists, and maybe some folks in this room were really hot on this a few years ago. It seems to have kind of gone out of fashion, unfortunately. But I still think it's an interesting problem. And are there other major algorithmic improvements that can reduce the obfuscated program size requirements? And this is still a challenge that we had, as you saw before. You know, gigabytes is getting quite a bit better, but you know, still not great. You know, particularly when you want to do things like iris comparisons and stuff like that. So the question is then, you know, how do we go and how do we put these various bits and pieces together? Well, there's been a couple ways that we've been going about it. You know, a major part of it is these lattice crypto-based approaches, where encryption, decryption, and so on, key generation, are primarily composed of linear transforms over large integer vectors and playing with various moduli and stuff like that. And we've been putting this into this PALISADE lattice crypto library. And we recently moved it off to palisade-crypto.org if you're interested in it. We've been building it over with our little cabal of team members since 2014 with a pile of money from DARPA and friends. and a number of US defense contractors. One thing that we decided on doing very early on was to use the BSD two-clause license. And I'll say this as someone who was in industry for 10 years and then became professor and then went back to industry to do a startup. For those of you that actually want to go and build open source libraries and have these things be actually used by people, GPL is the kiss of death. Whether or not you actually like it or not for religious reasons, a lot of folks in industry won't go near GPL licensed software, which is one of the reasons that we particularly explicitly chose something that's very open, like the BSD license or the MIT license and so forth. I'm not saying it's the best. I'm not saying it's the right way. I'm just saying that we chose this because we actually want people to go and use the software. I'm sorry? No. Okay, no. I don't know if you're laughing with me or at me. So, thank you. So, the PALISADE library, and we on purpose have been trying to make it as modular as possible. And this is kind of the other philosophy that we have is I'll hire anyone who, as long as they're as lazy as possible. And how do you be lazy? You basically reuse as much software as possible, right? Modularity is the key. And so what we particularly did, and this is a big part of how we were able to accelerate homomorphic crypto and obfuscation so much in PALISADE, is that we layer things. We layer things as much as possible. A very, very well-defined math layer. Even below there, a well-defined layer that ties into hardware. Above there, a layer of lattice operations. Above that, a layer of crypto. And then encodings and applications and so on and so forth. To make it as modular and as adaptable as possible with multiple math backends. And we just released a recent version in just a few weeks ago. So I encourage you to go look at it and or making it an independent project as it is also. And there's a number of things that we've done to, and kind of design decisions that we've done to kind of make PALISADE a little bit different from the perspective of software engineers. And this is how we think, we're thinking a little bit different in terms of PALISADE itself, is that the primary people behind it came from the US defense industry, where a lot of the funding is very hit or miss. We have to deal with something called sequestration, which basically means funding randomly gets turned off every few years because the Republicans and the Democrats can't get along. And so basically what we have to do is we have to make things as modular as possible so that we can have a lot of small steps and things like that. It's just the reality of how the business of research works in the United States. And so what we decided to do in that kind of harsh environment, as we call it, is that we decided to create something that we call the crypto context, which is a little bit different from the other open source libraries for Lattice crypto, which is basically, think about it as kind of like a blob that carries around all the various parameters for the use of crypto systems, and to basically make these things as object-oriented as possible. So it doesn't matter if you're doing attribute-based encryption or identity-based encryption or obfuscation or homomorphic crypto. You have the concepts of a crypto context, which basically holds all your parameters. And then you have the concept of ciphertext, plaintext, and keys, which doesn't really matter which scheme or which class of schemes you're using. They're all basically the same to make it as simple as possible. And so it generally tries to make these things a little bit simpler, where you can start by sending a bunch of crypto parameters, creating a crypto context from those parameters, and then enabling various kinds of capabilities you might want, like turning on encryption, turning on somewhat homomorphic encryption, or leveled somewhat homomorphic encryption, and going from there. And this is, I know this is something that was a part of the discussion during the first talk of the day about parameter selection and automating parameter selection. We see this also as a major issue too. And we decided to take kind of an all or nothing approach, and whether it's the best way, I don't know, or not. We decided to have one mode where, as we say in the US, we'll give you all the rope to hang yourself, which is a way of saying you can choose anything you want and shoot yourself in the foot if you don't know what you're doing. Or the much firmer approach, or nanny mode as we call it, which is basically to let people select a set of parameters that have been standardized in these various homomorphic crypto standardization organizations, and going from there to make it as simplistic as possible. And so then, once you actually go and create the crypto context and you start to go and select, for example, what actual operations you want to run, then it becomes much simpler to go and actually run things like key generation. So you go and generate a key pair, you go and, a key pair factory, you generate the key pair, and then you basically go and generate the various evaluation keys and things like that also. And similarly, you can start doing things like encryption and masking if you wanted to. And I don't really show this in the slides. As the first talk of the day showed, there's all different ways of encoding data with homomorphic encryption. Slots versus binary versus integer encodings and so on and so forth. We set it up so you can select the encoding you want to use in the crypto context and then just stuff a bunch of data in and then go and run. And then go and run and doing things like encrypting data using a particular public key pair and various plain texts and things like that to try to make it simple and model the other design paradigms that are out there for open source libraries for crypto. And the similar things with evaluation, trying to minimize mucking about with various evaluation keys and so forth using the various crypto contexts from there. And similarly with decryption, when you get things out at the end, without having to mess around with details of various encodings and stuff like that. And we've had a couple different applications of these kinds of things. I know we were talking before about these iDash competitions. I know there's one that's coming up in Bloomington next week. We participated last year. We had a couple applications that we supported for that. And there's a number of other things that are going forward. But as we're going through and doing various design work on PALISADE in and of itself, there was a couple design decisions that we were focusing on and looking at as we were doing the implementation. And that we also wanted to look at and be aware of when we're actually getting at some of the practicality challenges of applying these encrypted computing techniques. For example, applying the right compute model, choosing the right encoding and batching, determining the correctness requirements for parameters, security levels, standard APIs and parameter selections and so on and so forth. And there's a bunch of design decisions that we actually made. We're not saying that these are the best decisions. We're not saying these by no means are the only decisions. But after experimenting a fair bit, this is kind of the balance that we decided to go through as we're going and building the PALISADE library and applying it originally in these more defense contracting type activities. The other side of it too, which we're starting to look at, we looked at several years ago, and is still there, is the actual hardware acceleration of these kinds of things. And we see this as kind of being a big thing for two reasons. One, just because of the nature of the funding that we get for these applications, low power becomes a major issue. Not necessarily enterprise, but actually like embedded systems, mobile systems, and things like that. And so we spent quite a bit of time looking at low power hardware acceleration. For example, FHE coprocessors and so forth, programmed in C, and then operating over PCI Express to start as part of, you remember back, for those of you, I'm probably going to date myself by saying this, if you're programming on a 386 machine back in the early 90s, you probably got very familiar with math coprocessors and things like that. Well, those are still a thing. It's basically a daughter card that sits off the side to accelerate various mathematical operations. We were doing this a few years ago on the Vertex 7s from Xilinx as kind of like an FHE coprocessor once upon a time. And we have a couple publications that came out a few years ago in an IEEE journal for that. And kind of the lesson that we learned was that we were actually designing basically trying to take as many IP blocks as possible through the MATLAB tool chain, and then basically designing effectively what was a coprocessor with its own microarchitecture, microcode, and so forth that was actually sitting on top of sitting inside the FPGA and going from there, like a real honest-to-God daughter card. and then trying to generalize these various NTT, CRT type operations to take advantage of native hardware instruction sets and things like that. But then we started also getting these other issues of, as we start to take these very kind of very hard, computationally intensive challenges, which are hard enough for enterprise, starting to think about how we could actually deploy them on embedded hardware, sensor systems and things like that. So we have this notion in the US of what we call legacy systems, which is kind of a very polite, fancy way of saying really old hardware that no one uses anymore. You can't buy, but you already bought it, so you might as well use it. And so the question is, how do we actually go and deploy in these older systems, like 32-bit systems, 16-bit systems, computing at the edge, as we call it. And there were very large issues of configuration, deployment, hardware optimization, probably very, very similar to what was talked about in the first talk, the last slide of the first talk. And we started to look at various deployment architectures, particularly for embedded systems. This is not for enterprise. Enterprise is much easier. But for these embedded systems, about how we actually go and start to query the embedded system and build it out and go forward from there to actually start to do configurations and so forth. Particularly for model identification and deployment and so on. So that's kind of a brief tour of all the bits and pieces that we've been putting in PALISADE, driven primarily by these software obfuscation type techniques. And it looks like I went a little bit faster than I should have, but I'm very happy to take questions or anything else that we might have as we are going forward.